Hello, today we shall look at the structure of the molecular chain under molecular characteristics, which is we are doing the classification of polymers, and already we have seen polymers that can be classified on the basis of origin, on the basis of thermal response, on the type of polymerization. We have also seen under molecular characteristics how they may be classified depending on their molecular weight or maybe molecular shape or the chemistry and the repeat unit composition will be dealt with later on. And today we look at the next characteristic of a molecule, that is a structure of the molecular chain, how it affects the molecular characteristics. So under structure, we shall look at two types of polymers, that is homopolymer and copolymers. So when all the repeating units along a chain are of the same type, the resulting polymer is called a homopolymer. Chains may be composed of two or more different repeat units in what are termed copolymers. So let us look at this structure here. If it is a linear structure, one can look at it as a string of beads, which are the image looks somewhat like that, and imagine the molecular chains to be strings of beads which are there lying next to each other. So polymers may have a linear, branched, cross-linked or a network structure. So linear polymers are connected through the carbon atoms. The long chains are typically held together by the weak van der Waals or hydrogen bonding. These bonding types we shall see later on. Since these bonding types are relatively easy to break with heat, linear polymers are typically thermoplastic in nature. Heat breaks the bond between the long chains, allowing the chains to flow past each other, allowing the material to be remolded. Upon cooling, the bonds between the long chains reform, and that is the polymer hardens. So if between the molecular chains, if there are weak van der Waals forces or hydrogen bonding that is there between the molecular chains, then these can be easily broken by heat, and therefore such materials will normally be thermoplastic in nature. So some of the common polymers that form with linear structures are polyethylene, polyvinyl chloride, polystyrene, polymethyl methacrylate, nylon, and the fluorocarbons. So next we come to the branch structure, where we can see again the string of beads. If we look at the linear ones, now we can see that there are branches that are coming off the main chain. So branched polymers have branch structures of repeat units along the main chain. Branched polymer molecules cannot pack together as closely as linear molecules. So the forces holding these polymers together tend to be much weaker. So as we can see, because of the branching that is happening, the linear as compared to the linear polymers, these main chains cannot come close enough to form good amount of bonds between each other, and therefore such polymers, unlike linear molecules, do not have the holding forces between them, and therefore they are much weaker in nature. The chain packing efficiency is reduced with the formation of side branches. As I just mentioned, the chains are not able to come together closely, and so the packing efficiency is less, which results in lowering of the polymer density. So polymers that form linear structures may also be branched. So if even if there are linear structures, the polymers may also be found in the form of a branched structure. So for example, we can take high density polyethylene, and as compared to that low density polyethylene. So high density, or rather HDP it is called as, is primarily linear polymer, whereas low density polyethylene contains short chain branches. This is the reason why the highly branched low density polyethylene is very flexible and is used as packaging film, example saran wraps and plastic grocery bags, while the linear high density polyethylene, which is linear and therefore the molecular chains are able to come close to each other and form strong bonds, um, that is the HTP. It is tough enough to be shaped into objects such as bottles or toys. So we come to the third structure, that is the cross-linked ones. Cross-linked structures are formed when the branches on a polymer chain further react, connecting with the neighboring chains. The connection between polymer chains that form the network structures can vary in strength. Strong connection results from actual chemical bonds. So, if between the molecular chains, if one finds that they are bound by covalent or ionic bonds, then they are much stronger. While if there are connections of hydrogen bonds or van der Waals forces that are there between the molecular chains, then they would be much weaker in nature. So, polymer networks containing chemical bonds are called cross-linked polymers. The stronger bond makes most cross-linked polymers of the thermosetting type. So, since the cross-linking is quite strong, such polymers you will normally find as the thermosetting ones, unlike the other structures which were thermoplastic. Often, this cross-linking is accomplished by additive atoms or molecules that are covalently bonded to the chains. One example of cross-linked polymers is vulcanization or vulcanized synthetic rubber used in automobile tires. The rubber is vulcanized by cross-linking so that they form covalent bond between the molecular chains and become much stronger, and which could then be used in heavy duty applications like automobile tires. So then the next structure is the network structure. Networked polymers are complex polymers that are heavily linked to form a complex network of three-dimensional linkages. Multifunctional monomers, when we say multifunctional monomers, what function means having lots of double bond, triple bonds. Higher the number of bonds, higher the functionality of the polymer. So, multifunctional monomers that are there, which have got unsaturated, the bonds are there, double bond or triple bond, forming three or more active covalent bonds. So, such bonds will open up, and if they are able to form covalent bonds and make multi or other three-dimensional networks, then such polymers are called as networked polymers. These polymers are nearly impossible to soften when heating without degrading the underlying polymer structure, and are thus again the thermosetting type of polymers. These materials have distinctive mechanical and thermal properties, and the examples are epoxies, polyurethane, and phenol formaldehyde. And these are the polymers that belong to this group. An example of a networked polymer formed by weak connections. So, such a network can also be formed by weak connection, unlike the ones that we just mentioned, wherein covalent bonding is there. If we have weak connections, then it will form a networked polymer, which is something like a gel formed by pectin. This natural network polymer is the basis for jellies and jams. So one can imagine that polymers are not usually of only one distinctive structural type. For example, a predominantly linear polymer may have limited branching and cross-linkings within the structure. So majorly it will be linear, but there'll be some limited amount of branching or sometimes cross-linking between the molecular chains. So the polymer are not usually only of one structural type. So with this we come to the copolymers. If polymers are built from two distinct monomers, they are referred to as copolymers. The four basic structures are random, alternating, block, and graft. If the two monomers are randomly ordered, then the copolymer is of the type of random copolymer. So one can see in the diagram shown under A, where the beads are of different colors, blue and say red, and they are randomly arranged. There is no distinct pattern there. Whereas in B, one can see it is alternating. One red and blue beads are alternating with each other. So the beads are representative of the monomers that are coming in an alternate fashion. So in an alternating copolymer, each monomer is alternated with the other. Um, so it can be generalized as AB pattern, which is written as AB n times, as in the case of polyamide such as nylon 66. So nylon 66, which we shall learn in detail later on, is an example of alternating copolymer consisting of alternating units of hexamethylene diamine and adipic acid. Because of the complementary reactivity of the monomers, they have to alternate. So since there is because of the reactivity, complementary reactivity, the monomers will always form an alternate pattern in this case, in case of nylon 66. We shall see this later on in much details. So the next type of copolymers that might be found is when the homopolymer units are linked together via covalent bonds. The resulting single chain macromolecules is called as a block copolymer. So if there is a homopolymer unit that is there, and such homopolymer units are then linked together via covalent bonds, as one can see in the figure C that is shown, it's a homo, the blue one, if there are say 4 or 5 that are shown over here, that's a block, and the red one also forms a block. If these blocks are connected via covalent bonds, then in that case it is called as a one can say a block polymer. In block copolymers, more complex repeating structures are possible. For example, AAA, BBB, AAA, BBB type of pattern, where you'll find blocks of two monomers appearing repeatedly one after the other. So the next type is the graft copolymers, and these are created by attaching chains of a second type of monomer on the backbone chain of the first monomer type. So one can see that the main chain is of the blue bead of say one type of monomer, and the branch that is attached to the main backbone is of the second monomer type. So this type of a copolymer is called as a graft copolymer. So with this, we have seen all the structures in which a molecular chain may appear. We have seen homopolymers as well as copolymers and their various structures. So with this, we come to the end of this lecture. Thank you.